Makaku once commented that we will require to revise our course readings on the start of the universe. Everybody has been enthusiastically anticipating a specific picture, which has now been made public. This picture from the James Webb Telescope uncovers strange cycles in the universe that challenge our logical understanding. Since the send-off of the telescope, not just have our hypotheses on the universe's beginnings been tried, but indeed, even exoplanets have begun to challenge our comprehension of material science, totally flipping our ideas. What new circumstances and answers can researchers find because of these incitements? We are right now seeing a complete disturbance of the old standards in science. The James Webb Telescope is reforming our impression of the universe, and each new picture from this wonder of space investigation is pivotal. James Webb, the telescope's namesake, would have been glad. Webb was not a researcher but rather came from a business foundation. He comprehended the meaning of space investigation for mankind. As head of NASA during the 1960s, Webb advanced space travel altogether, sending off the Apollo program and supporting space tests. Today, researchers are dumbfounded by the capacities of the telescope named after this trailblazer. The pictures are so clear and sharp that they take our breath away. Interestingly, we have complete examinations of exoplanets some huge number of light-years away. The telescope is uncovering to our logical local area that they have been relying on obsolete discoveries and thoughts for a long time. At first, numerous researchers are encountering vulnerability and uneasiness as all that they trusted in may now be discredited. Mio Kaku, a famous astrophysicist from the USA, is one analyst who is hopeful about these new improvements. Kaku has long contended that our past speculations were deficient. The powerlessness to join the universe of subatomic particles with the universe of shaped matter alone demonstrates that we have not completely perceived major cycles in the universe. Presently, exoplanets are likewise breaking the laws of material science. It's shocking. At first, only old cosmic systems didn't fit into our cosmological models. Then came dark openings and colossal designs more than 13 billion years of age when the universe was evidently in its outset. Presently, even planets defy our past understanding. The most recent pictures from the James Webb Telescope show exoplanets that challenge our past thoughts regarding planetary data. The telescope reconsidered probably the most unusual known exoplanets with its sharp eye and special cluster of spectrometers. The instruments can separate even the slightest light signals into their singular parts, breaking down hints of components, gases, proof of water, and boundaries that reveal the size and circles of far-off planets. In the process, Webb finds more peculiarities, limits, and the most insane planets. One striking illustration of these unthinkable universes that oppose the guidelines of material science is K2-9b, an ultra-hot Neptune circling so close to its star that its surface temperatures are sufficiently high to part water atoms into nuclear hydrogen. The extreme nearness to its star prompts a peculiarity researchers call environmental blow-off, where the planet's climate is literally blown away from the star. This revelation is interesting among all known planetary environments and presents a critical challenge. Webb finds so many exemptions and limits that it's genuinely inconceivable. K2-9b is so weird that it's extremely difficult to classify and represents a glaring exception to all the rules we've established. Another universe that panics researchers is WASP-76b, a giant exoplanet with iron raining from the sky on its night side. The planet circles its star in a tidally locked orbit, resulting in very hot and cool sides. Metals melted and disintegrated on the hot day side harden into iron on the far side, then tumble to the ground like rain. Researchers are dealing with extreme conditions that stunningly illustrate the actual processes on exoplanets and bring up more questions than answers. Especially fascinating and baffling is the revelation of planets circling their stars in the opposite direction to other planets in the same system. Such discoveries force cosmologists to re-examine theories about the dynamics of planetary systems and the forces that determine their orbits. WASP-17b is an example of such a world. This exoplanet, found as part of the wide-angle search for planets, WASP, is a huge gas giant resembling our Jupiter but circles its star in a retrograde direction, opposite to the star's rotation. This was thought logically impossible according to current theories of planetary formation, which suggest all planets in a system should circle in the same direction as they formed from the unique protoplanetary disk. One hypothesis that explains such circles is that gravitational perturbations from neighboring passing stars or other gigantic planets can drastically alter a planet's orbit after its formation. Another possibility is a gravitational dance between several huge planets can drive at least one into a retrograde orbit. Curiously, we do not need to look past our solar system to find bizarre planets. In the Kuiper belt, we find the dwarf planet 2018 VG18, which sweeps have demonstrated to be uncommonly dim and red. Webb spectrometers reveal that this planet is likely rich in complex organic compounds, which researchers call tholin. Despite its extensive size and eccentricity, 2018 VG18 remains without an official name since its precise orbit is yet to be determined. Its probable composition, rich in organic substances that are the building blocks of life, and its strange color do not match other dwarf planets in the Kuiper belt. This raises questions. Where does this planet come from? How did it form? And why is it so hard to see? Because of its significant stretch, observing 2018 VG18 precisely and over an extended period is very difficult, even with our best telescopes. It is perhaps the third largest dwarf planet after Pluto and Eris, and specialists see it as a critical object for understanding dynamic processes in the Kuiper belt and the evolution of the nearby planet group. Drifter planets, planets without a star, are another fascinating possibility. Would you believe there are planets without a star? Planets typically form in the dust and gas disks left over from star formation, remaining gravitationally bound to their star. Anyway, drifter planets show that this is not always the case. These cosmic introverts float unreservedly through space without a star. But where do they come from and how do they survive in the unfriendly cold of space? Drifter planets can form in various ways. One common method is ejection from their original star system due to dynamic interactions with other planets or close stellar flybys with gravitational forces sufficient to haul the planets out of orbit. Another possibility is they formed as separate objects in a star-forming region but without sufficient mass to start nuclear fusion processes like stars. This could also explain the presence of objects called jumbos, which are Jupiter mass-like objects that didn't gain enough mass to start nuclear fusion and become stars. Jupiter, the largest planet in our planetary group, was barely short of the mass required to start these processes. The James Webb Telescope stunned researchers once more when it found 80 such drifter Jupiter mass planets in the Orion cloud. The peculiar part of this revelation is the almost unbelievable truth that these 80 planets have formed 40 double systems, meaning 40 pairs of drifter planets circle each other inside the restricted space of the Orion cloud. This is strange and logically unlikely. The sheer number of these planets might be due to the Orion cloud being one of the most intense star-forming regions known. Anyway, more detailed examinations showed that these objects are not genuinely planets but somewhere between planets and brown dwarfs in terms of mass. This suggests they are failed stars, as brown dwarfs are among the smallest stars known. However, what processes in the Orion cloud are responsible for these failed stars that behave like planets, freely moving through the universe in binary systems? This is another extreme test for our researchers. These objects probably form a class of their own, pushing the limits of our astronomy. It is conceivable that such large free-floating objects are significantly more common in the universe than we thought. They might be ordinary but are rare to us because we were previously unaware of their presence. We have not had the option to distinguish exoplanets in the profundities of space for very long, and concentrating on them has always been challenging. The James Webb Space Telescope represents an achievement in this regard. We are excited by these revelations, but researchers are becoming overwhelmed by the new peculiarities and inconceivable findings. Nothing is as they expected. Has science reached an end? The James Webb Telescope was made to fill gaps in our knowledge and confirm existing theories. Rather than closing gaps, its findings are tearing new holes in what we consider bits of truth. As some now say, the crisis web has triggered marks the end of our old science. As Maya Kaku said, we must revise our course books. But what should we write in them now? No coherent new answers have yet been found, and scientists are frantically looking for new explanations. Unlike its ancestor, the Hubble Space Telescope, which primarily sees in the visible and ultraviolet frequencies, JWST is enhanced for infrared observations. This capability allows it to look through astronomical dust clouds, study the formation of stars and galaxies, and even characterize the atmospheres of far-off exoplanets. One of the primary scientific objectives of JWST is to unravel the mysteries surrounding the origins of the universe by concentrating on the light from the most distant galaxies. The telescope can provide insights into the early stages of cosmic evolution not long after the Big Bang. This includes understanding how the primary stars and galaxies formed and what they meant for the development of the universe over billions of years. As well as studying the distant universe, JWST is poised to upset our understanding of exoplanets, planets circling stars beyond our local planet group. The telescope's sensitive instruments can examine the environments of exoplanets and detect key components, for example, water, methane, and carbon dioxide. By doing so, researchers aim to identify conditions conducive to life and better understand the potential for habitable environments beyond Earth. This capability addresses an enormous step forward in our quest to find signs of life elsewhere in the universe.